Hello and welcome to all to this lecture series on basic thermodynamics. This is lecture 3, concepts of work and heat. So let us begin. First of all, we need to see the energy and energy interactions. The energy are comprises of two kinds, microscopic and microscopic. What is a microscopic energy? Microscopic energy is the internal energy, that is basically the energy that is within the system, within the constituents of the system. Okay, and microscopic energy is the bulk kinetic and potential energy. That means when there is a system and when that whole system is having some velocity, or means it is having some kinetic energy, or when it is above some datum and when it is at potential energy, the whole system means the bulk kinetic and potential energy, that is the microscopic energy. And the energy which is within the constituents of the system, means within the molecules there is some kind of energy in the form of sensible energy, in the form of temperature change, or latent energy in the form of phase change, then chemical energy in the form of some chemical reactions, or nuclear energy in the form of some nuclear combinations or destruction, basically anything like that at the nuclear level. So that it comprises the microscopic energy, and the microscopic energy is the bulk kinetic and potential energy of the whole system. So energy interactions can take place in three ways, that is the mass interaction, work interaction, and heat interaction. That means that when the mass, work, or heat that crosses the system boundary, then we can say that energy interaction can take place. Okay, it can be into the system or it can be out of the system. That we will see how we counter all those things in the later slides. Okay, then first of all, very important concept of ideal gas, that frequently you will come across this word in your reading also, and while solving many problems also, that air is an ideal gas, or an ideal gas having this properties, all those things. So first of all, you need to know what is this ideal gas. The ideal gas, any gas can be assumed to be ideal gas under the assumptions that the ideal gases, in the ideal gases the intermolecular forces are negligible. Moreover, however, this does not happen anything in any gas, that the intermolecular forces cannot be negligible, but we consider in the case of ideal gases that the intermolecular forces are negligible, and the volume occupied by the molecules of the gas is neglected as compared to the volume of the container. However, this is also hypothetical, this cannot happen, because if there is a gas contained inside a container, so it will surely have some volume it will occupy. But in the case of ideal gas, we assume that the volume occupied by the molecules of gas is neglected as compared to the volume of the container. And under which conditions any gas can be assumed to be an ideal gas? It should be, the pressure should be less and the temperature should be high. So any gas, any real gas can be assumed to be to follow the ideal gas equation, and all those means to behave ideally under the conditions of pressure should be less and temperature should be high. So some of the key points with respect to the ideal gases: all the substances which are gases in normal conditions, means which are gases in normal conditions, will always be taken as ideal gas. Example, there is oxygen, there is nitrogen, carbon dioxide, and many other gases are there which are, or many other substances are there which are gases in the normal conditions, so they will always be taken as an ideal gas. Water vapor will always be taken as an ideal gas till mentioned. Means for this you can see that if any problem you come across the word of water vapor, means water vapor going through any changes of state or through any process, so you can, when there is given the water vapor, so you can automatically think that it will behave as an ideal gas. Otherwise it would be mentioned that water vapor which will not behave as an ideal gas. If nothing is mentioned, so you can always assume that water vapor behaves as a ideal gas. Okay, and then another thing is steam. Steam will never be taken as an ideal gas till mentioned. Means if at any problem you come across the word steam, that the steam is your working fluid, so it will never be taken as an ideal gas till mentioned. If it is given that steam behaves as an ideal gas, so then you can take. Otherwise, if it is given the working fluid is simply written as steam, so you will never consider it as an ideal gas. These are very important points, please make a careful note of it. Okay, then gas constant. See, we have seen this is the ideal gas equation, that PV is equal to mRT, where this P is the pressure, V is the volume, M is the mass, R is the characteristic gas constant, and T is the temperature. So characteristic, and T is the temperature, that is the absolute temperature in Kelvin. Okay, so R is the characteristic gas constant having a unit of kilojoule per kg Kelvin, and if we write it in this form, we will have PV is equal to mR bar T. Okay, where R bar is universal gas constant. Okay, please make a note correction here, that this is not M, this is N, that is number of moles. This is number of moles. Okay, that is mass upon molecular mass. Please correct this. Please sorry, this is to be corrected. This is not M, this is rather N. Okay, please make a correction here. This is N, this is not N, this is the number of moles. Okay, then where this R bar is known as the universal gas constant having the unit of kilojoule per kilomole Kelvin, and it is having a fixed value of 8.314 kilojoule per kilomole Kelvin, and this R, and the relation between R and R dash is equal to R bar by M. R and R, relation between R and R bar. And the ideal gas equation for the various processes is, already you can see that this is the ideal gas equation, PV is equal to mRT, where this R is the characteristic gas constant, and this depends upon the mass or the molecular mass of the ideal gas which we are considering. This R bar value is fixed, that is 8.314, and for calculating the R for each substance, it is to be divided by its molecular mass. So the ideal gas equation for various processes, PV is equal to mRT, and since M and R are constants, since M is also a constant and R is also a constant, so we can take that PV by T is a constant, or we can write that P1 V1 upon T1 is equal to P2 V2 by T2, where PT is the absolute temperature and P is the absolute pressure. So please make a note of this, that this P is not a gauge pressure. This is the pressure which is measured with respect to absolute zero or absolute vacuum. This is not a gauge pressure which is measured above the atmospheric pressure. This is the absolute pressure, and T is the absolute temperature in Kelvin scale. Okay, so these are some of the ideal gas equation for various processes. Some of the processes you might be knowing that there are some processes that are constant volume process, also known as isochoric process, or isometric process also it is. Please make a note that it is also known as isometric process. So P1 V1 by T1 equal to P2 V2 by T2, when V1 equal to V2, so you will have P1 by T1 equal to P2 by T2. Similarly, in the case of constant pressure or isobaric process is also known as isopiastic, isopiastic process. Please make a note of it. Sometimes these words are also given, that in the isopiastic process, or in the case of our constant volume, it is written that isometric process. So you might also you should also know these names, so that you do not get confused when these terms appear in any, while reading anything or while solving any problem. If you come across these words of isometric or isopiastic, so please don't get confused. They are constant volume and constant pressure processes. Okay, and in this case P1 equal to P2, so V1 by V1 by T1 is equal to V2 by T2. In the case of constant temperature process, that is also known as isothermal process, temperature is constant, means T1 is equal to T2, that means P1 V1 is equal to P2 V2. In the case of adiabatic process, that means in which no heat transfer take place, not energy can take place in the form of work transfer, but in the case of adiabatic means no heat transfer taking place. In this case, the ideal gas equation is PV to the power gamma is equal to constant, so you can have that P1 V1 power gamma equal to P2 V2 power gamma, and when you change this, when you use the equation of PV is equal to mRT, and you find out the relations, so you will get these two relations also, that T2 by T1 is equal to P2 by P1 to the power gamma minus 1 upon gamma, and T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. And when this gamma this is the gamma, that is the ratio of Cp by Cv. Cp by Cv, that is the specific heat at constant pressure and specific heat at constant volume. That we will see in the like future slides, in the next slides. And when this gamma is replaced with n, that is the polytropic index in the case of polytropic process, so this PV to the power n equal to constant is a equation for polytropic process. And in this, if we utilize the same the PV is equal to mRT, the ideal gas equation, so we will come up with these equations. Okay, so you can pause this video and you can also note down all these relations. These are very important in solving the problems. Okay, then the one more important concept is there, that slope of isothermal and adiabatic curve on PV diagram for ideal gas. See, you have seen that for an isothermal process, the PV is equal to constant is the ideal gas equation, and when we will differentiate it, we will get PdV plus VdP equal to 0, and the slope, you know that this is the P and V curve, and when you will draw the slope, that means the dP by dV. So from this equation you can get dP by dV is equal to minus P by V. And for the adiabatic process, you have seen the equation is PV to the power gamma is equal to constant, and when you will differentiate it like this, so you will get this equation, and when the slope that is same, the dP by dV, you will get minus gamma P by V. So you can see that this equation is the slope is minus gamma times of this, means the slope of adiabatic process is always greater than the slope of isothermal process for the ideal gas, because for the ideal gas always this gamma is greater than 1. So you can see that whether it is an expansion process or whether it is a compression process, you can see that the adiabatic process slope is always greater than that of an isothermal process. So this is very important concept, please make a note of it. Then let's move on further. The representation of various processes on the PV diagram for an ideal gas. How various processes are represented in the PV diagram or the property diagram, which is also known as property diagram. So in this, you can take a general equation that PV to the power k is equal to constant. Then for different values of k, the processes nature of process changes. See, if you put the value of k equal to 0, that means V power 0 equal to constant, V power 0 equal to constant, or P equal to constant. That means it becomes a constant pressure process or an isobaric process. So isobaric process will be, this is PV, and isobaric process will be a line parallel to the volume axis. So this is a k equal to 0 in the case of expansion also, and in the case of compression also. Similarly, if you will put k equal to 1, you will get PV equal to constant, that is a isothermal process. So isothermal process, and k equal to n makes it polytropic, k equal to gamma makes it adiabatic, and k equal to infinity makes it an isochoric or constant volume process. So you can see these, k equal to 0, k equal to infinity, this is constant pressure, this is constant volume, and this is, you know that in the last slide we have seen that the slope of adiabatic process is always greater than the slope of isothermal process. So this is k equal to gamma, that is adiabatic, and this is k equal to 1, that is isothermal, and in between these will come k equal to n. Generally this can, theoretically talking, this k equal to n can come anywhere between these two, but for the general occurring processes, the value of n lies between 1 and gamma. So this lies between this isothermal and this adiabatic process. This is for compression. Similarly, you can see for the this is for expansion. Similarly, you can see for the compression process also, this is k equal to infinity, k equal to 0, k equal to 1, gamma, and this n line between these two. Okay, so you can, because I am telling you in this much detail because these kind of questions have, or this graph has many times appear in various examinations. Okay, this graph has generally been provided in the types of match the following, and they have provided this curve graph with the values of curve as 1 2 3 4 5, and they have given the values of k, various values, and then they have asked to match the column. So please do not take these concepts very lightly. You have to follow them very seriously. You have to follow them, and you have to make a very important note of it. Okay, then let's move on. Then comes the work. What is work? The technical definition of work is said to be done by the system if the sole effect on the things external to the system can be reduced to raising of weights, though weight may not be actually raised. That means that if there is a system and whatever the processes are occurring inside the system, if the sole effect of those processes can be reduced to raising of weights. Means by all those processes, if anyhow any weight could be raised, means a kind of mechanical work is generated. That means then you can say that the work is said to be done by the system. But if it is not necessary that the work that the weights may be actually raised. It is just an hypothetical concept that whatever the processes are occurring inside the system, if it is capable of generating a kind of mechanical energy or mechanical energy which is capable of lifting the weights, so in that case we say that the work is said to be done by the system. And the reverse happens where, so in that case it is said the work is said to be done on the system. Okay, so it depends upon the direction of because this expression is that the del W is equal to F dot dr. So these is all the vector quantities. As you can see, there is a dash upon them, so these are all the vector quantities. So see this you can see that it depends upon the direction of force and as well as the displacement. This is the displacement and this is the direction of force. Okay, if displacement is 0, then work is not necessarily 0. If displacement is 0, then work is not necessarily 0. If displacement is 0, then work is 0 only for the conservative forces. Conservative forces means which are non-dissipative forces. See, if you consider a very common example in terms of mechanical engineering, if you will, that concept you might be aware from the class 11 12 physics also, that the concept of friction. You say that there is a friction, and while the friction always opposes the positive work, means friction is basically a kind of negative work which generally opposes your desired work. So if the work is done against the friction, so that work will never be means if the displacement is 0, and in doing the work which includes or which includes the friction force, so that means when you are doing the work against the friction force, even if the displacement is 0, then the work is not 0, because friction is a kind of a dissipative work. It is not a conservative force. Okay, it is a dissipative force. So you cannot say that. So this is the example of simple example, and there are many more examples. You can look for them at any standard books, but this is the basic concept what I am going to trying to tell you, that if the displacement is 0, the work is 0 only for the conservative forces or the non-dissipative forces. Okay, so then there is a closed system analysis. Under the area under the PV diagram, when projected on the volume axis, gives the work interaction for the closed system. See, there is a closed system, and when the closed system there is any process, so when this process is projected on the volume axis, and the area under that PV diagram gives the work, that gives the work interaction for the closed system. So the conditions for this equation to be satisfied, or the area under the PV diagram when projected on the volume axis, will give you the work only in the case of closed system. And the quasi-static system means quasi-static, I already told you that, which is the process which is occurring infinitely slow, or the pressure should be close to the piston. If it is a piston cylinder kind of arrangement, then the pressure should be given close to the system, because if it is quasi-static, that means the pressure is same throughout the system. But if it is not quasi-static, then the pressure will be varying throughout the domain. It will be varying, and the pressure which we will consider here, this is a P, the pressure which we will consider here, that should be close to the piston. Or if it is a quasi-static process, then it will be same throughout the domain, then it is not a problem. But if it is not a quasi-static process, then the pressure which is to be considered here, that should be close to the piston. This is very important concept. Please note it down. Then some of the important points with respect to work. See, work is a path function. That means if we are reaching from one point to another point through two processes, and the first and second, the initial and final positions are same, but if we are following two different paths, so the work involved in both the processes or in both the state transition of states will be different, as work is the path function. This is all the things, these important concepts, they have been explained in more detail in the future lectures. Just make a note of it as it is, as I am telling you, and just understand it theoretically what I am saying. I will explain you all these things in detail in the later lectures. Okay, so work is a path function, it is an inexact differential. This already I have told you what is inexact differential in the last lecture. Please go through it and understand it there. And it is not a property. It is not a property, that means it does not depends upon the initial and final position. Okay, what is a property? That is the any characteristic of the system is the property, means it is a which is defined at a point, that is a property, but it is not defined at a point, and it is a path function. Okay, it is dependent on the past history. These are all our points are just converse of what I have taught you in the last lecture about the properties. Properties was not dependent on past history. This is also dependent on the past history, and it is a boundary phenomena, means the work can only be identified when it crosses the boundary within the system or just outside the system in the surrounding, if anything is happening. So we cannot say that the work has happened or not. Work and also the heat, they will be identified only as positive, negative, means done on the system or by the system only when they crosses the boundary. So these are the boundary phenomena, and these are also the transient phenomena. Transient phenomena means they are changing with time. Okay, so they are then the expressions for this non-flow work in various processes. It is non-flow work is also known as closed system work, PDV work, or boundary work. See, if you have a constant volume process, please, while going through all these for all these expressions, please make a note of or remember this expression, that del W is equal to P into dV, and these del W and dV are the vector notations. Please make a note of that. This is a vector quantity, that it depend on, it has the direction also and it has the magnitude also. So please make a note, remember this, that del W is equal to P dot dV. Okay, so in the case of constant volume process, that isochoric or isometric process, I already told you dV, that is the change in volume, is 0, so the work is 0. And in the case of constant pressure process, also known as isobaric or isopiastic process, the pressure is constant, that means work is equal to P into V2, that is final volume minus initial volume. In the case of constant temperature process, isothermal process, work is given by C ln V2 by V1, which is also written as C ln P1 by P2. These expressions you can derive yourself, and where C is P1 V1, which is also equal to P2 V2, and which is also equal to MRT, because in the case of constant temperature or isothermal process, P1 V1 equal to P2 V2. And in the case of adiabatic process, you can see that this is the equation I already told you, PV to the power gamma equal to constant. So when you will derive this, that P dV, when you will take that P dot dV, if you integrate it yourself, you will get this expression, that work is equal to P1 V1 minus P2 V2 upon gamma minus 1. For the polytropic process, this PV to the power n equal to constant, and I already told you that ideally the value of n can vary from minus infinity to plus infinity, but for the general occurring processes, these values lie between 1 and gamma, that is the adiabatic index. Okay, so when you will yourself, you will do that integration of PdV, and you will within the limits of 1 to 2, you will surely get this expression as work is equal to P1 V1 minus P2 V2 upon n minus 1. And in this case, you can see that n must not be equal to 1. So you have seen that I haven't put the equal to sign here. This means that n cannot be equal to 1. If n becomes equal to 1, that work will be infinite. Okay, then you can see that quasi-static expansion and compression work is the most efficient process. Quasi-static expansion and compression means that work obtained during the quasi-static expansion is the maximum. Please correct that this is not minimum, this is maximum. Okay, work obtained during quasi-static expansion is maximum, and the work required to be done during the quasi-static compression is minimum. This is important, please make a note and please correct this. This is maximum, that work obtained is maximum and the work required is minimum in the case of quasi-static compression and quasi-static expansion. These are some of the statements that you might not realize their importance while reading this, but these statements appear in the form of some of the essential regions questions that you might see in the exams. They are just made from these statements only, so please make a note of it. They are very important statements. Okay, then next is how you will realize these processes. I have told you many processes: isochoric or constant volume, constant pressure, constant temperature, adiabatic, polytropic. But how you will realize this process in a real life? So this is the realization of various processes. That means constant volume process, that process carried inside a rigid container. Means if you have a rigid container whose volume is not changing, so that can be taken as a constant volume process. Constant pressure process means if the piston is free to move, if you have a piston cylinder arrangement and if that piston is free to move, means you do not have any obstruction to it, to the movement of the piston. If the piston is free to move and the external forces remain constant, that means you can consider it as a constant pressure process. Isothermal process means, see, if the isothermal process means that the temperature change should not be there. If it is to be realized for single phase, then it must be carried out in a very slow manner. Means the process it is a kind of a quasi-static process. If it is a quasi-static process occurring, then it can be termed as an isothermal process for a single phase. But if it is to be carried out in a very fast manner, if you need to carry out an isothermal process in a very fast manner, then it must be carried out for a phase change of the substance. So this is the best example I can tell you, that while boiling a liquid, say water, you boil the water and the temperature keeps on rising, till it reaches 100 degrees Celsius, and when the 100 degrees Celsius temperature is reached, the water boils, and when till the liquid water gets converted into the vapor, the temperature remains constant at 100 degrees Celsius. That means that it is an isothermal process, but that is carried out for the phase change of the substance that I have told you as water. So this is the very best example of the isothermal process carried out in a very fast manner. Okay, then adiabatic processes. Adiabatic process means no heat transfer taking place. So normally it is carried out using insulation. If you have insulation, if you are using, then the process can be considered an adiabatic process. But if it needs to be carried out without insulation, if you need to carry out any adiabatic process, means the process in which no heat transfer should take place without insulation, then it must be carried out in a very fast manner. Otherwise, if you do it in a slow manner, then some amount of heat transfer will surely take place. Then what is a polytropic process? Polytropic process, for which this n lies between 1 and gamma is followed, then heat transfer, see, that means in the case of isothermal process, there is a constant heat transfer. Means the heat transfer is throughout the process, the heat transfer is there, and in such a manner that the temperature always remains constant. But in the case of adiabatic process, the heat transfer is zero. So in the case of polytropic process, something which should lie in between these two processes, something middle way of these two processes should occur, in which the n lies between 1 and gamma. So in this process, the heat transfer must be there. But it should not be sufficient enough to maintain the temperature as constant. So if the polytropic process, you can see that it is just a middle way process between this isothermal and the adiabatic process. If in the polytropic process, if heat transfer is not taking place, it will become an adiabatic process, and if the heat transfer is taking place in such a manner that the temperature remains constant, then it will become a isothermal process. These are very important realizations, how you will realize which process under the real conditions. These are very important. Okay, then let's move on. Another concept of heat. We have seen work, now we will see heat. Heat is a form of energy that is transferred by the virtue of temperature difference. This is the very simple definition and very exact definition of heat, that if someone asks you what is heat, the heat is a form of energy that is transferred by the virtue of temperature difference. This temperature difference is the only driving force for the heat energy. Any other driving force is not there for the heat. Heat cannot flow if any other driving force is there other than this temperature difference. If the temperature difference is there, then surely there will be a form of energy which is known as heat. Okay, and the magnitude of heat will depend upon the difference of the temperature. But even if there is a slight temperature difference between the two states, then surely there will be some amount of heat transfer between them. Okay, then this is heat transfer denoted by Q. This is directly proportional to the mass, directly proportional to the temperature difference, and there is a constant term which is introduced. This is C, that is known as the specific heat, and this MC together taken is known as heat capacity. And this you can see that C is equal to Q by M dt. The unit is kilojoule per kg Kelvin or kilojoule per kg degree Celsius, because this Kelvin or degree Celsius does not make any sense, because this we are taking as dt, that is the temperature difference, which is same for numerically same for both the scales of Kelvin and degree Celsius. Then Cp is the specific heat. There's the C, then the Cp with the subscript P is the specific heat at constant pressure, and Cv is the specific heat at constant volume. Specific heat is the amount of energy. What is the specific heat? How you would define it? The specific heat is the amount of energy required to raise the temperature of unit mass of a substance by unit degree. Means if there is a substance and you need to raise the temperature of the unit mass of that substance by unit degree, means you need to increase the temperature by unit degree of the unit mass of the substance. So then the amount of energy required is known as specific heat. And specific heat at constant pressure, you have seen there are two specific heat: constant pressure, constant volume. So specific heat at constant pressure is always greater than specific heat at constant volume, because this Cp includes both the internal energy as well as the boundary work, whereas Cv includes only the internal energy. This is important. Why Cp is greater than Cv? This is asked in the exams also, and sometimes in the interviews also. Then why this Cp, that is the specific heat at constant pressure, is greater than specific heat at constant volume. So this is the explanation for it, that Cp includes both the internal energy as well as the boundary work, whereas Cv includes only internal energy. Okay, then we have seen that the variation of Cp and Cv with the temperature and all. See, as the temperature increases, both Cp and Cv increases, but gamma decreases for the polyatomic gases. Polyatomic gases means gases having more than one atom, means yes, multi-atomic gases. Both Cp and Cv increases, but gamma decreases. You can see that this is Cp and Cv, and what is this gamma? That is the ratio of Cp by Cv. So this increases and Cp and gamma decreases for the polyatomic gases, but for the monoatomic gases, means the gases having a single atom, both Cp and Cv remain constant, hence gamma remains constant. And this is the R. You can see that this is R is Cp minus Cv, and this is always constant for every kind of gas. Okay, then let's move on. This is the important these are the important points with respect to heat. These are all the same points as I have told you in the case of work transfer, that they are path function in exact differential, not a property, dependent on the past history, boundary phenomena, and transient phenomena. These are all the same points as in the case of work. Then there is a convention of internationally accepted convention of heat and work. What are these? Heat, when it is given to the system, when the heat is given to the system, it is taken as positive, and when the heat is taken out of the system, it is taken as negative. This is the not the convention that I have been following. This is the convention which is being followed internationally. Okay, so do not try to mess with these conventions, otherwise your answers will get affected, maybe magnitude wise, or maybe just by the sign of negative positive, your answer will get altered. So do not try to mess with these conventions, and do not try to make your own convention. Just try to remember them, because these are the internationally accepted conventions of heat, that given to the system is positive and taken out of the system is negative. And similarly in the case of work done, that work done by the system is taken as positive and on the system is taken as negative. So I have given them different colors, so you can just easily make out that given to positive, taken out negative, work by the system is positive and on the system is negative. So these are the important concepts that I have told you regarding the work and heat. In the next lecture we will start with the first law of thermodynamics. So for any queries or any comments, you can write down in the comment section below. If you want to make these lectures in the Hindi, so they're on the public demand or on the viewers demand, that can also be done. So that you need to tell me in the comment section. Okay, so just follow these things and just practice the questions which I am which are related to these topics which are covering on a daily basis, so that it does not get a burden upon you in the last time during the exams and all those. Okay, so thank you for watching this lecture and have a nice day.